All right, it's my pleasure to have Mike Zink here with us today, giving a seminar. He's the Paris Professor of Geophysical Sensing Systems in the Department of Electrical and Computer Engineering in the College of Engineering at the University of Massachusetts, Amherst. I know it's long. He serves as co-director of the Paris Center for Atmospheric Research. His research focuses on multimedia systems, cyber infrastructure, and large-scale sensor networks for geophysical sensing. He's the PI of NSF Open Cloud Testbed project, and talking about this today. And it's a true pleasure to have Mike both here as a colleague and also as a welcome.
Thank you. Thank you very much. Yeah, absolutely. I can only second that. It's great to be here. I might be distracted by a wonderful view. I'm coming from the Northeast, so weather's always a little bit of a different thing here. Thanks for having me. I want to talk a little bit in our work, as Eva said, on the Open Cloud Testbed today. But I kind of thought, but this would be sound more like a body wash commercial if I say rinse and repeat. But this is about build, measure, and repeat. I think something you all are familiar with because we're all kind of been spending a lot of time together and in different other projects of building research infrastructure, especially for the SciSce community. And I also want to make this clear up front. I'm going to talk about work that is not related to Pegasus because all of you know what Pegasus is. So, speaking with Mats and Eva in the room and Rajiv in the room, I talk about Pegasus, I would just get myself in trouble. So I want to talk about other things, but I also want to make clear, or really want to point out from the beginning, I've been working with you and Eva and your team for the last, 10 years or something like this. It's been absolutely wonderful collaboration to do these things. And hopefully we can discuss how some of the work I'm presenting here ties into some of potential future work. Okay, so I want to talk about the Open Cloud Testbed and what I think of, how the future of experimental computer engineering might turn out in the future. I'm coming back to some of the work we just recently did on that side. So overview. Again, we have a wonderful overview of this area you guys are here in here. I want to talk about the three R's and introduce them. Nothing new for you guys, but just coming back to that and see how that impacts research these days. I think in all research areas, right? In all science-based research areas and also in our area. And then talk a little bit about infrastructure, where we host the Open Cloud Testbed, the framework under which we make resources available, and then really go into the details of OCT, stands for Open Cloud Testbed, just making things a little shorter here. And then bring in a couple examples that we and some collaborators with us have been using OCT for some research, but also for building tools that others can use in their research, and especially in respect to the 3 R's. So what I'm talking about when I mean the 3 R's is repeatability, reproducibility, and replicability. And I think there's this, repeatability. I tell this to my grad students all the time, right? I don't want to see a graph that has just one measurement point. You need to have 10, 20, whatever where your confidence interval goes. So we all, I think, do repeatability in our daily do things over and over again, pretty much on the same basis, right? And that's really with our own data. So rerunning an experiment under the same condition, not much changes from one, usually not too much changes from 1 hour to the other. Reproducibility is, getting consistent results with the same input data over time, where the computational steps, methods, and codes, and conditions of the for the analysis are relatively the same. Right, but not always exactly the same. So there's a little bit of a change there. This is often what we do in terms of we hand over things to colleagues. We try to create baselines from other work, and so I think that's it. And replicability is actually that next step. And I try this analogy, which is, for example, TCP, transmission control protocol, right? Been research going on for the last 50 years or something like this. If you talk about TCP congestion control, there's how many TCP flavors out there? 200, something like this, right? When you look at congestion control, you want to actually see that, TCP Tahoe is doing the same, or is performing congestion control as much as TCP Reno is performing congestion control. And so you have some reproducibility, right? So you can say that there's actually where you have two different flavors of the same approach, but you can say you can at least demonstrate the same behavior. It doesn't have to be identical, and that's important. When I prepared for this talk, I looked a little bit of the National Academy of Science and Engineering. What is it now? The medicine, right? Report, and looked at. They have a report on this, and they talk about a couple of things which I think is really important when we do our work. Which it took me a moment to realize. Well, science is self-correcting, right? So I looked back and thought, what's another good example? Well, maybe Newton and Einstein. Not that I'm a physicist and have a really good idea about all this, right? But if you look at Newton's laws are totally valid until you get to speed of light or close to speed of light, right? So you can say there's this thing where you say, well, Newton is right, or you can say Einstein is right, or both are right? So it depends a little bit, and so I think that's always what we have to do when we try to reproduce results, right? Sometimes we cannot reproduce results because things change, or there's new radical approaches that changes things, the view on certain things, right? That's important. And I think it's a very important thing to keep in mind, and it can also lead or uncover that there's certain problems. Maybe there's a problem with the study, and it's fine. I think it's totally fine to say, I think these some other group might have done really their best, but if you look at this and have new data or whatever, you can see that changes. Right? So that's important. Obviously, what's important also is the sharing of code and data. Right? We're talking about this. How do you make that possible? And I think that's a career-long challenge for all of us is with all that. But the more I think we share information as a community, I think the easier all these 3 hours become. And then I think we have all seen that, and I totally agree with that. There's often not a singular application, right? In science and research, yes, the core, natural laws, there's probably true and false, but others, I think true and false is not really that clear-cut line. So we have to keep in mind. And so what came out of that study, and I think that's interesting and really resonates with what we've been doing over the years, is that you need hardware, right? Without hardware, I think pretty much every science needs some instrument. For us, it's often lots of computers and networks and disks. For others, it's telescopes and radars, whatnot. And so you need that. You need tools, right, to analyze the data and work with the data, and then repositories to archive that data and make it available to others. And so what I think what I want to talk about today is more about the hardware and the tools. There's a lot of other people who look into the kind of repository work and curation of data. Okay, so today I want to go from kind of the bottom up and talk about the hardware, our testbed, the tools, and then give some examples we have been working on in the past. So first of all, a little bit of a, how do you say that? A little bit of a complicated term. The MGHPCC is the Massachusetts Green High Performance Compute Center. So this is a compute center that is a collaboration between, I have them here so I don't forget all the members because they're growing, Boston University, Harvard, MIT, Northeastern, the University of Massachusetts system, and then recently also Yale. And so this is a pure research data center. In this data center, like you could say NERSC or something, there's nothing administratively for the universities is running there. It's all for high performance computing for any kind of research jobs that are people wanting to execute there. 15 megawatt facility with 10 megawatt of power that's available for computing. Pretty reasonable or substantial. It is green because it's very interesting. If you ever come and visit me, I'll take you down to Holyoke. Not the greatest city in Western Massachusetts, but it's the first planned industrialized city in the United States. They put a dam in the Connecticut River and put canals in the river. and the canals are different elevation, and so they used to power mills in with that. And now they use the hydropower to power the computers that are in the data center. So that's why it's a green data center. So a little side note on that. What's really nice is it brings a lot of, it kind of has some gravity, right? Because it brings people together from different universities that are all interested in research computing, and it has a lot of different clusters in there. So I can talk, for example, in our side, we have our own compute cluster for the universities, for the UMass system that is used, but then also the Open Cloud Testbed is installed in that cluster. We also, it's probably not a surprise for everyone, we also have a new cluster coming up. It's called ACAR. That is the AI compute resource. That's a state initiative where the state of Massachusetts has made a significant investment to support AI research. It's happening pretty much everywhere, I guess. Okay, so that's, machine room with space, with racks, with a lot of space for computers. Now, once you have all these computers in there, right, you want to make them available to the community. And so what we decided when we started planning for the Open Cloud Testbed, that we decided to make our hardware available under the Cloud Lab framework. Some of you are familiar with Cloud Lab, right? So, and we did that because I've been a PI, well, not only, but I've been a PI on Cloud Lab, so I'm very familiar and I'm very well connected with the team. But also we said, we want to make bare metal servers available. Why not use a framework that a good chunk of the research community is also already used to, and don't start with something completely new. And Rob and team over at Utah were, happy to support us on that side. And so that's how we could integrate. So Cloud Lab itself is also a scientific infrastructure for cloud research, has different clusters across the country, which offers thousands of courses with certain, if you do cloud research with certain specializations in the hardware that are offered, right? From, low power systems to more storage oriented systems. And so when we looked at this, we thought, and with my colleagues at Northeastern, we thought, field programmable gate arrays, so another type of accelerators, are becoming more and more popular. At the time, there's a Slingshot at Amazon, and there's Catapult at Amazon, and there was Microsoft also offered FPGAs in their commercial clouds already. Problem is, as we all know, for cloud research, you cannot mostly not use commercial clouds because they limit you to the accessibility. You cannot look into the inner workings and all. And so we talked to the community, and then they said, we want actually have access to these FPGAs to do research with FPGAs in data centers. And that's how the whole idea came about. So coming back to Cloud Lab, you can build your own cloud on certain hardware, right? It's bare metal, so you can install pretty much whatever on these servers what you'd like to, and then you can do what I would call systems research on a cloud distributed. Again, the Open Cloud Testbed, there the goal was to expand that by adding FPGAs to this network, and so we extended Cloud Lab with another cluster in MGH-PCC. It has not only nodes that contain FPGAs, it has also a bunch of other servers, which we got through a donation and made this also available to the research community. So if you don't need FPGAs, you can use our cluster for other experiments, but mostly what we're supporting is really the use of FPGAs in the research. And then what we did. And again, this was a demand from the user community, is these FPGAs, most of them are network attached. So you can actually really do, a lot of, processing directly of data that's coming directly off the network in what most people now call smart NIC way. But there's other applications that you can do. Again, so there's a difference between, we have a couple FPGAs that are only attached by the PCIe bus, which is typically similar to what you use with a GPU or anything, where you can run, specific. You can use it as an accelerator, but there's kind of no kind of in networking or computing that you can have. And then we have a bunch of network attached FPGAs where you really can, do processing once the data comes off the wire, or you can do processing before you ship it out. Currently, this is always growing. We have a really nice collaboration with AMD. They're really supporting us with sometimes giving us new FPGAs or prototypes that we can install. 36 and counting is the number of FPGAs we're making available. Maybe a little bit of a repeat. So what is OCT, right? It's well, this always helps me also thanking our sponsors. So this is an NSF-funded. There was an NSF-funded community infrastructure project, Zink project. Again, an FPGA testbed, originally for cloud research. What I think this is probably what we all have seen with our projects. You often have an idea of what this is for, and then users are very creative and use it for completely different things, which is wonderful, right? So that's great. For cloud research, networking research, I certainly see these days security and AI, obviously. And then the idea is also that because before, I think what we observed is that a lot of research groups had FPGAs, a couple of FPGAs in their lab. Right? And that's fine. I think there's sometimes even a good reason, because you want to sometimes be able to yank this thing out and reset it and then do all these kind of things. But with putting it in a community testbed is nice, because then people work more together and share information. It's kind of a forcing function. I think that is quite good. So it's accessible to a wide to a huge community in that area. You can make it flexible and scalable. And I actually will, in a couple of slides, talk a little bit about how you can actually make it scalable beyond the Open Cloud Testbed. And we had to go through a little bit of a discussion before we did that, because with bare metal provisioning, you find that you provide information you provide tools where you have to trust the users, because you can actually now really implement things right on the FPGA. The latest FPGAs we're getting in there have 4 200 gig interfaces, so you can kind of do stuff that's not great. So that's one of the things we have to figure out. And that's, if you have built testbeds before, where it was really important that our data plane is as much isolated from the regular internet as possible, so any misconfigurations cannot go out to the world. It's pretty much available for everyone who works in academia worldwide. I know this is totally small and hard to decipher, right? But I want to just point out that these things take time and planning, and they grow. And I think this is again where I want to come back to what I said about MGH-PCC, where we have these different clusters together and these different research communities. Anirban and Kamal, see in the back, Fabric, right? So we, for example, have a direct layer 2 link into Fabric, and so we can reach out wide area or otherwise. I don't know where this link is going out exactly, but through UMass, MGH-PCC holds also an AtlasNet 2 cluster. It's for the LHC project, and we have a tight connection to that LHC cluster, right? So we can actually do, and we're working with those folks right now, and some in-network processing for when data is coming out from experiments from LHC. We can go to our own local cluster, and then obviously when we designed that, we also thought about how do we do the networking. Again, we're going up to some FPGAs now that can combine support up to 800 gig. So you need a good network infrastructure, which keeps us on our toes, because now we have to replace also some of the switches because they cannot support this. So here's the FPGA side, and then we have some other machines, other servers in there that are non-FPGA that everyone can use for other types of experiments. How do we set that up? So here's a little bit more of just an FPGA focused view, where we have a bunch of, if you're familiar with FPGAs, they're kind of older now, Alveo U280s, that all are connected with two 100 gig interfaces. We have a bunch of nodes that have FPGAs and GPUs, right, older type, but it's kind of interesting. I will show where this can come interesting for some research. And then we have, the couple that only have an FPGA as an accelerator, where you don't have any network connectivity. So quite a variety. And we're getting actually new V80s onboarded right now. Again, they have high throughput, which should be very interesting for the network research community. Interestingly enough, AMD is still working on the Mac side of that, so to support the networking side. So we're working with AMD on that and getting that going, and can support this fully as a network connected interface with all the bandwidth. Okay, so let me mention one more thing, because I have my fabric friends here. So I forgot a while ago. So a couple of years, it was right, when did you leave? 2 years ago, 3 years ago, something like this. A couple of years ago, NSF reached out to us and said, you've done this work with the FPGAs. Fabric is interested in putting FPGAs in, and so we work together, and also, including FPGAs in Fabric. There is, I forgot the exact number, 20 plus U280s also in different nodes across the world in Fabric. And so now what is a nice new feature, relatively new feature, is that you can actually not only do cloud-based experiments in a cluster that's local, that's in one location, but you can also set up a slice that is wide area and can do any type of experimentation on that side. And there has been a very nice collaboration between the two teams. And I'll make, well, I can actually mention this right here, because it has some challenges. On our side, our servers are bare metal servers. So once someone allocates the server, the experimenter has the server totally to themselves. In Fabric, it is virtual machines. Now, if you have virtual machines, virtualization on regular hardware, it's no problem anymore. We're doing this for 20 years now or whatever. But if you have specialized accelerators, that especially FPGAs, you cannot visualize them, right? And so how do we do that? And so that was a really nice collaboration with Mert and others at Fabric to figure out how this can be done. Some back and forth, but it's certainly possible, and brings a new feature to both test beds and brings them a little bit closer together. Okay, and I think the important messages here can go from a cloud environment to a wide area network environment, if that's interesting for researchers. Okay, so what is he talking about? So let's make a U-turn and go back to the 3 R's, right? So reproducibility, reproducibility, and applicability, as I mentioned before. And so when we do our research, I think one important thing is to keep in mind, what are all the pieces that have to be put in place, right? Pegasus AI, we talk about this in many, many different directions and avenues also, right? And so when you go back in sometimes even with the matter of a month, right? Can I really take that information? Can I run the experiment again and at least, kind of repeat it, right? Without running into many problems. And I think that's something that is important and it should be in everyone's head when you design these test beds, and when we, not just you, we as a community, design these test beds and think about making the tools we need in addition to just the hardware. And so I want to point out a few things where different groups I've been working with have put some thought in that. Again, with Cloud Lab, obviously, the one important thing is when you do resource allocation, right? Because you run an experiment on a certain slice. Servers, network, storage, and so on. And so if you wanna repeat that, you might somehow want to make sure that you have pretty much the same hardware as close as possible. And so Cloud Data has this concept of profiles that is really, in the end, nothing else than a script that tells you how to allocate your resources. And then you can, with that, execute that script again and should get the same resources. Fabric has a similar function with Fablet, right? So that's important. What's interesting here is that you can actually do this you can now maintain this and version control these profiles on GitHub, right? So you can actually go out there and have a version. If someone makes a change, you can how can you say that? You can track that change. You can document that change, and someone else another user can be aware of that, right? And so I think that's important because if you are not aware of these changes, repeating things will be very difficult, and you might need to be able to personally reach out to someone, right? If you have that version control, you can look at this, and you can then also look at if you, for example, want to repeat a paper, the result that's been presented in the paper. You can look at, hopefully there's a good documentation or a good description in the paper or in the artifacts, tells you what version was used, or you can at least go back and say, oh, this paper was published at some point in time, probably this version before it got updated, right? So you can work based on that. So that's really kind of something I thought for me, it was an important lesson, is kind of how can we make these tools and the artifacts we use for these tools, also, how do you say that? Keep track of time, so to speak, and keep track of the changes, right? I mean, it's on one side, it sounds like a no-brainer because we all do that with code all the time, right? But I think code is not the only part where this is important to keep in mind. With FPGAs, and I'm sorry I didn't talk too much about FPGAs because I should have said in the beginning, I'm not a hardware guy, right? I just try to build stuff and then I talk to the hardware guys. How do we do that, right? But with FPGAs, it's a very different animal to pretty much everything else you program, right? Programming FPGAs is hell. So what was important for us also is that what we wanted to do, and then with Saranga, we have a really great FPGA engineer who does a lot of work on creating a tool flow, right? So being able to create what people usually call a bitstream, so a program that you can implement on an FPGA, and have that environment available to the research community. And what we did here is actually we took a couple of servers that are dedicated just for the development of these FPGA programs. And similar to what I said before, that we package VMs that bring up that whole tool flow. And then you can build whatever you want to build for to run on an FPGA. Same thing here, you can kind of, if you do that carefully, keep versions of these VMs. You can then say, oh wait, this was a bitstream that was built in 2023 with these tools, and you can go back and use those to replicate it. Or it was in 2025, or you want to build on something on top of it and maybe take a recent VM, right? So that's important to keep these tools available and make it easier for the research community also to use the FPGAs, but also track back and go to things that have been done in the past, right? So, but that is something that is challenging, right? Because you say, what you're talking about, it's challenging for all of us because things change all the time, right? But you really have one person who's kind of dedicating a good chunk of his time to just keeping this workflow up to date. There's new tools coming on. You see already here, there's YDIS, there's this regular G compiler, there's Pink, which is a Python-based tool that can create bitstreams, right? These all have to be maintained and have to make sure there's licensing and all these kind of things that have to be kept in place to keep this up and running. Now, I told you about the nice collaboration we have with Fabric. We actually then agreed at some point in time that, since you have this running on OCT already, why don't we also make this available for the Fabric users? because then they can build bitstreams also for the FPGAs that are in Fabric, and I think there's no problem on our side if anyone else has any FPGAs they want to build bitstreams where they can use this workflow to make this available. Another thing that I struggle with where to put this slide, right? Because it's a little bit hardware, but it's also service, and has to do with making measurements that I think is sometimes important for research results, because I think power and the use of energy for computing has become super important. I just last month or whatever, I flew into Dallas in DC, outside DC. When you come in from the north, there's data centers growing like mushrooms right now. It's just crazy, right? And if you think about all the power consumption, I truly believe it's going to be a huge problem. And if it is already a problem, it's just becoming a bigger problem. And so what I think is important, we really have to be able to also characterize in our analysis, in our experiments, what power efficiencies do we have with systems, or find power inefficiencies. And so with MGHPCC, we were lucky to put highly controllable power distribution units into the racks, where we can actually measure very accurately the power that's going into each of the servers. And with that, you can do fine-grained power measurements and analyze how energy efficient a certain algorithm is, a certain approach is, right? And I'll show you in a couple of slides, for example, what's the difference between running something on an FPGA compared to running something on a GPU. Most people will tell you, oh, FPGA is more power efficient. Yes, that's true when you just look at the accelerator. But if you put something into a larger system where you have GPUs that are optimized to run large batch sizes, which you cannot do on an FPGA, for example, the story becomes very different. You cannot do that if you're not able to have a really, I would say, for lack of a better term, objective power measurement, right? Because what you also see is the tools that the vendors provide you. There's one tool for the FPGAs. There's another one for, at least for NVIDIA GPUs. They're not really measuring power. They're making kind of simulations and emulations and assumptions. And so how accurate are they actually? So really knowing what's coming out of the outlet is important. And we built a fantastic student at the time that built a database and a visualization system for that, so you can actually observe that, have the data, use it for analysis. Okay, so that's kind of the tools, and now I finally want to come to a couple of examples. Sorry, that shouldn't be animated here, but so this is for mostly for networking research, but since it's also in network processing, I think it's kind of on the border between networking and computing / cloud research. P4, so programming protocol independent processors. Sorry, so the last P here is something that has been caught quite a bit of attention over the last 10 plus years or so, and what we used is we built up on top of an Vitis tool or AMD tool that allows us to offer users the way to program FPGAs with P4. So basically, on a high level, you turn them into a smart NIC, and now you can all kind of different things, and it's really interesting for like prototyping, offloading of network functions, customizing the network stack, and what we do with that is then supporting network research. Not only on OCT, you can do this also on Fabric, because that's the same type of FPGA. So here's an example. This is again using the OpenNIC shell and VitisNet from AMD. We created a tool flow to deploy this on FPGAs. For those who are a little bit deeper into the kind of networking and hardware side, this allows you to dynamically replace functions, right? So you can have, if you have a certain networking function, well, let me back up for a second. I told you before, programming FPGAs is a little bit different than other processors and accelerators. So you build a bitstream, you load it on the FPGA. Once the bitstream is on there, it's kind of almost like an EEPROM in the old days, right? So once you want to get rid of that, you have to recycle the FPGA, right? And so that's, if you want to do something dynamically, that's not great. But what you can do is you can have these dynamic functions and partial reconfiguration, so you can change the functionality while you have this particular bitstream loaded on the FPGA. And so that gives folks who are interested in that area quite a bit of flexibility. If you're really interested and want to go into the details of that, paper is a couple of years old. We have on different functionalities we have implemented as examples and that people can use. So all the way up to, and that's maybe something I should mention that makes it interesting. For the folks who are more familiar with P4, this is also Tofino switches, right? So you can also do this processing in switches. Because it's in ASICs, it's a little bit more limited. So what we've kind of tried to find out is, can you make things a little bit more complex? So for example, we allowed more complex computation, right? Because that's not possible with the ASICs implementation in the Tofino switch. And I think that's really good, because if you do that on the edge where your FPGAs sit, not in the core of the network, that really supports in-network computation, right? So you can do any kind of operation that you can, more complex mathematical operations that you can think of, and do something where you can really offload the bus and the CPU or GPU from this type of computation, right? So that's, I think, an interesting and important aspect that you do not get with the off-the-shelf P4 hardware that runs in, or that you can get as a switch. Okay, well, that's a part on the networking side. Continuing that is when you do experiments, right? I talked about power, but we're getting more and more into time is also very important. I mean, this is one. Timing has always been important, right? If we talk about distributed systems, you want to know what happens where as exact as possible, and in many cases as exact as possible. Timing is also important for security and a bunch of other applications. And so I don't know, we looked into network a while ago, right? And with Kong, just remember that, right? So we looked into, can we use the FPGAs to put, to do shim headers, right? So to shim something right behind your Ethernet header to have custom information, right? And so you can do, I think the sky's the limit on that side. You can put timing information in there if you have highly synchronized clocks on your system, maybe PB, for example. You can actually see how long a data takes to travel through over a bunch of servers through the network and so on. That has a lot of implications. You could imagine that you have a setup where you come up with a new protocol and you want to repeat, or you want to analyze how a certain TCP or whatever works. Now you can do this with, here's the old version, this is the timing I get out of it. Here's a new version, this is the one-way delay I get from this, right? Doesn't have to be like this. Doesn't have to be necessarily just timing information. You can also do anything of counting, anything of queue state, all kinds of different things you want to use your packet as an information carrier and do it in bed, so to speak, or in network, right? So that's important. Now, I think an important argument might be, well, you can do this where you have this type of hardware, but what happens if you go outside of it? Right? And so we thought a little bit about this, and that's really a problem, right? The moment you go outside of your network that supports P4, you cannot do this anymore. But what you can do is you can actually have ingress and egress areas, right? Where you start having this additional information added to your packets. It can, for example, sorry, I don't know why this is so unfocused. So you can add this information once they enter, for example, your data center. If you're really interested in measuring timing information in your data center, once they leave the data center again, P4 can help, or you can remove that information and just have a regular Ethernet packet going on. Right? So you can at least use it in portions of your network to do accurate timing measurements and any kind of information you want to have while your information is traveling through a data center. Now, I just talked about PTP. This is some work we're just doing right now. Actually, if you want to do one-way latency measurements, you want to have really detailed timing information. And so even if you have a physical hardware clock, PTP-controlled hardware clock on your FPGA or on your SmartNIC, the problem these days is that, I'm sorry for, there's a little bit of complexity that I'm ignoring right now, but even when you do this, the precision time protocol is still a daemon that runs somewhere on your server, right? So you're trying to synchronize a clock or an oscillator that runs here. But to do this, signal is coming in from a PTP signal is coming in. But then you go all the way through your system to the kernel and then back. And that takes time, and that takes unpredictable time if you want to have nanosecond accuracy, because it depends on what's going on your bus, with your CPU, and so on, right? And then you send that back to synchronize your oscillator. And that has, it takes many cycles and has implications about the accuracy. And so I have a student, he wouldn't let me go and say, we want to do this on the FPGA to figure that out. And so what we do now is actually he implemented this all on the FPGA to do the synchronization of the hardware clock layer. And here's some preliminary results. And what you see here is actually host CPU load, right? Increasing CPU load and the latency clock cycles that it takes to when in clocks you call discipline, right? You discipline your oscillator to the clock. And what we see is here, obviously, nicely, because that's another thing, benefit of the FPGA is predictable, right? It's not multitasking anything. It's kind of in the circuit, right? So you have it there. If you run, this runs on a 250 megahertz clock. If you have it there, this stays constant because it's independent of how much CPU load you have. If you do that with a PTP that's running in the kernel, and then going back to discipline the clock on the FPGA, you can see how many more cycles you need to. And what happens during these cycles, right? Your clock drifts, and so you don't have the accuracy. There's two places where the green one, and that's why it takes less cycles, is when we have a core that's only dedicated for the PTP daemon to run, and the other one is where you share it. But you still see what's coming in here is also that the more load you have on the CPU or the cores, is there's also more going on the PCI bus. That's another deterministic delay that you get. Right? And then pretty much similar approach where you again do this with one core and see how the load goes up. Not too much new information. Coming back to the power, right? We also looked into comparing when you have, this is just ResNet 50, so and machine learning inference where you want to detect objects and images, right? And see the difference between the power consumption when you implement this on an FPGA compared to a GPU. And I had a lot of back and forth when I worked with my student on that, and it is the power consumption on the device, but then the device doesn't really, exist in a vacuum. It's in a whole system. And so you have to keep, I believe you have to keep that in mind when you do your analysis, because that all consumes power, right? And so while an FPGA is consuming potentially less power than a GPU, depending on how you set up your end-to-end workflow. I said workflow. That has implications on the power consumption, and you want to be able to identify and characterize that. So I think that's important, and I think that is something which we've been looking into right now. This is a very specific case. I still am in the process of thinking of how can we generalize this, because this is really for one application and two specific types of hardware. But I think we have to do this in more general to see. I think there's no one size fits all, and but we have to make these comparisons to be smart about what loads do we run on what accelerators and what type of hardware. And this is hopefully my last graph. I'm going to show you. This is a little bit more complex. What we're showing here is actually, so if you want to do image detection, object detection in images, how many frames per second can you do on this, or how many images can you do? And this is actually frames per second per watt. So if you can do more frames per second per watt, the better, right? Because then you're more energy efficient. If you can do less, the worse. And so we're looking here actually into different configurations of the FPGA, and the power measurement that is been done by the tool that AMD provides, which is kind of a simulation estimation tool, and the actual measurement of that the smart PDU performs, right? And so here, the interesting thing is here, takeaway messages that we see that there's a trend, right? Because what we measure with the outlet is really the whole power consumption of the whole system, right? While XPutil is kind of representing the power consumption of the FPGA, right? But it's not an actual measurement. But here we can actually verify, since we have the smart PDU, that it's a good approximation, right? Frames per second is much higher in this case because frames per second per watt, I apologize, is much higher when we do XPutil measurements, because it only is the power that the FPGA consumes, while here, this is the whole system, right? And now, I apologize, I don't have a graph, but now you can actually compare that, right? How is the whole system in frames per second per watt you're looking when you do this on a GPU, right? I actually have the graphs somewhere. If someone's really interested, we can look it up later. But now you can actually look at this, and what you also see is what is the power consumption on the device, but what's the overall system consumption, right? And so that helps you with also building maybe more power efficient systems around that. We see in more and more ARM architectures coming up with GPUs because you don't need the high power, or don't want to use too much power on the FPGAs. This is too many examples. This is for Kamal. So I think the last part is really also, and Kamal started something really good, and I was happy to participate in that. Is actually, sorry, I shouldn't say. We also thinking about this in Pegasus AI quite a bit. Apologies, but how comes AI into this whole, a cycle of the 3 R's, right? And I think we have an idea. We don't know completely how this works, and we're identifying some of the weaknesses, right? So what you do is, if you want to reproduce someone else's work, right? Well, even if I want to reproduce a paper from like I wrote last year, I probably would use AI and say, tell me quickly what I did last year, right? And so you take your paper, you have maybe publicly available codes and data. So it's coming back to one of the very early slides, right? I told you how important it is to have this available. An AI augmented experiment interface makes it really nice to you to collect that information and then start getting feedback from the AI on how do I even start an experiment if I haven't done it myself, right? Coding assistant, because often if I don't necessarily have the code and data sets available, I have to reproduce that somehow. And then what's really important, and I think that's what we see at the moment, is you still need domain guidance and results. Unfortunately, Baron is not here yet. We can talk to him. He's here tomorrow. My colleague from UMass, who looks in. He's a bioinformatics guy who looks on this side. But for some of the experiments, depending on how far out you go in the domain sciences, right, it's hard for the AI and it's hard for the non-domain scientist to judge how good you reproduce a result. You really need this information. And then, if you do this, interestingly, you have kind of these different phases, right? And where can AI come in? But we haven't eliminated. Thank God we haven't eliminated the human completely. Right? And this is I think Kamal's awesome slide table here. She looked at different research applications, right, in molecular dynamics, genomics, and then DBR is a congestion control algorithm for TCP, and assessed how much the effort is when you do this with AI, what the benefits of this in speed up is. I think the most important roles are here: speed up, right? So can I say these are estimates right now? Yeah. Right? So 4 to 6 times speed up, a relatively small amount of money. Right? Now, again, I would come back to what I said before. It would be interesting to see how much energy that also are needed. Not only our energy, but also the energy to get the AI going on this. But I think that is something I think we're all trying to wrap our brains around these days with tools. But also, I think it's important to think about how do we have this interaction with AI, or how do we use AI to help us with not only generating new research results and new discoveries, but also helping replicate what has been done in the past, because we need that all the time for baselines and comparisons. So I think that's something important. I just talked to some people that think about healthcare, and what I found interesting is they talking about having different AI agents talking to each other. Should we create different agents? Right? Do we have a Pegasus agent and a Fabric agent and maybe an OCT agent who talk to each other when we do this? Something interesting to talk about, and hopefully in the next couple of days we can discuss this kind of things. That would be great. Okay, hope I didn't bore you too much. If you're interested in this, here's a link to tutorials and accounts for the Open Cloud Testbed. If you wanted to do some work on that, or just reach out to me. I have to thank a large group of people. Right, this is not all. I did the most little piece of it, but this is some work I did with all these people involved. And obviously, most important, my grad students are doing all the work. I'm just getting the benefit of giving the talks. A wonderful team I get to work with. And if you're really interested, maybe you want to have Claude give you an excerpt on all the several publications we have in this area. Okay, with that, I want to thank you for your attention, and I'm looking for. Yeah.
And there are applications sure network science, on more science engineering. So from the actually engineering using single node scenario, single site scenario. Yep. Like I would have imagined like there would be like domain specific computations being done on FPGAs for some kind of biology applications, right? So are those use cases coming through, or is it still in the stage where we're trying to figure out the technology itself to do this work?
Yeah, so yes and no, right? I think they're not coming through to us. I'll tell you what the challenge is. For some of them, you need to be at the instrument or at the you cannot do it in the data center, right? Two examples is wireless networking, 5G, 6G, and so on. Software radios you can nicely do with FPGAs, right? But it's kind of hard to do that if you are, I mean, you can do some simulation, but it's hard to do that if you're miles away from your content, right? Same with physics, right? So the folks I work with at UMass, we have FPGAs, and we have used Fabric and OCT FPGAs for SciTech. I don't know if you know what SciTech is. It's a protocol where they're trying to tag packets to get them scientific data, to get them through research networks in a faster way. Right? That's our domain. It has nothing to do with physics. You can use that for any kind of. They have FPGAs at CERN, right, where they do processing of the data that comes off the collider. But they need to do it right there because the data rates are so insanely high that there's no, even today, you cannot think of shipping them over any network. So that's unfortunately a little bit of a dilemma, but I think that's also where I said in the beginning, right? I think there will always be a way where people have hardware on their benches or in their offices because they or at their devices because they need it right there, and some of that you can more centralize. Speaking of that, what I would like to see in the future is that maybe for some of the prototyping, people could use OCT before they then really implement it in a production scenario. Just hope that answers your question.
Other questions?
I have one. You showed one slide where you're taking in those power measurements to compare how, what additional resources you had to add to enable that? Or did you have to just add more hardware for that? Like if you were to enable that on Fabric, what would be?
You need smart PDUs. Okay. Yes. So that's I think, I mean, scratching my head now because I have to think about the protocol, right? Because if you get, PDU X and we have PDU Y, it's probably speaking a slightly different language to get the information off. But otherwise, I think you could just plug it into what Hakan had built with Grafana, with InfluxDB and Grafana to get the information off. Now there is a little bit of we had a long discussion of that, of what data you make available, right? Because if you make all data available, I could probably see what your experiment uses for power. I do not find that a huge problem, but some people, are a little bit more protective about these things. So that's maybe one thing to think about. Otherwise, I think it's just an exchange of. I don't know what PDUs you have right now, Rex. Maybe they feel.
I don't know either, but I was.
It's probably a nerd question.
Yeah.
Great. Well, let's thank Mike. Thanks so much.
Thank you for coming.
Thank you.